Welcome back to the classroom. My name is Mr. Wong. In today's lesson, we're going to be covering the 2011 HSC Physics paper, question 29. This is for Module 7, inquiry question number 3, which is about the quantum model of light. And this actually relates back to Planck's equation, and that's what we're going to be talking about today. So let us begin. Okay, so with the question, it says, or 29a, it says calculate the number of photons. So what I want to know is the quantity of photons available for a given wavelength, which in this case is 450 nanometers. What we need to do before we do the question is just make sure we convert that into the appropriate SI units, which is -9 or 10 to the -9 meters. And then it says which are required to transfer a total amount of energy of 1 times 10 to the power of -3 joules. So that's the energy total. But obviously what we know is, according to Maxwell's equation, energy comes in quantized packets. So although I get a total energy of 1 times 10 to the power of -3 joules, there might be a whole quantity of photons that add together to make up that value. What we need to do firstly is work out what's the individual energy of one packet of photons for that given wavelength. So I know that frequency can also be found using velocity times frequency over wavelength. So frequency can be written as velocity over lambda. And if we have the scenario where it is the speed of light, because it's a photon, it would be c over lambda. So I can substitute that formula in. E equals to h c over lambda. And if I do that substitution, I have Planck's constant. So there's that. And I have multiplied that by the speed of light. Let's just change that, that's 34. And then the wavelength is 450 times 9 to the 10 power 9, -9 there. So that's what we have. If I then put that into my calculator, I should be able to work out approximately the amount of energy of an individual packet of photon. So let's just have a look as I do that calculation. So approximately speaking, it's, or actually if we write the whole number, 4.417333 continuous repeater, like so, 10 to the power of -19 joules. So that's the amount of energy an individual packet would have. If I then change the color, because I want to find the number, so the number n of photons would therefore equal to 1.1 times 10 to the -3. So that's my total energy. So I'm doing total energy divided by the energy of one photon. So 4.41733333. I'm going to use the entire value I got just then. And so what I find is, if I then put it into my calculator again, is the total value is approximately, because the lowest significant figures given to me is 2. I'll round it off to 2 significant figures. It's 1.2 times 10 to the power of 15 photons. So that's how many photons with a wavelength of 450 nanometers. That's how many photons there is in an energy distribution of 1 times 10 to the power of -3 joules of energy. So that's what we have there. So on to question B, which says a 1W, we can say 1 watt of beam. So a watt of beam of energy transfers 1 joule per second from one point to another. with reference to the particle model of light contrasts a 1 watt beam of red light with a 1 watt beam of blue light. So we can look at, the easiest way to look at it is wavelength of the colors, okay? If I was to look at the visible spectra of light, so if we had the visible spectra, on one side we have blue light, and on the other extreme it's red light. The way that they're differentiated between another is the wavelength of the light source. What we know is blue light has the small wavelength, or the smallest wavelength of visible light, and red light has the longer wavelength of visible light. Now, why is that significant? Well, as we look at the previous equation that I derived, so from V equals to F lambda, now V is just the speed of light. So that's a constant there. So if I rearrange this around, we can say that F is proportional or inversely proportional to wavelength. What that means is as wavelength increases, in the case of red light, might do a label for red. So if red light has that, that means its frequency is low. So according to the formula E equals to HF, red light would have a low energy because it has a low frequency. Okay. Blue light, on the other hand, we'll go back to blue. Oh, that's indigo. We'll go dark blue. Blue light has a small wavelength, which means it will have a high frequency because it's inversely proportional. So that means it will have a high energy and low or high frequency. So obviously, what does that actually mean in the context of what we're talking about here? Well, it effectively means that in order to generate the same amount of energy in the beam, I need a much higher quantity of red light photons than I do with the blue light photons. Because blue light carries more energy individually, the quantity required is a lot less in comparison to red light. Okay. So I will just write that properly. So before I do that, I'll just have to scribble some of this out, because it's a little bit too much doodling around. Okay, so it is 2 marks. So technically speaking, we don't have to go into a lot of detail to compare the difference. But, you know, just for simplicity's sake, just for clarity's sake, let's try and give as much detail as possible. So what we know is, so as blue light has a longer wavelength, I'm just going to write it as lambda, then red light, blue will have the higher frequency, hence higher energy per photon. Okay, and you know, if this was like an additional 3 marks instead of 2, you could then put in the formula equals HF to kind of justify what you're talking about here. That's fine too. Okay, so what we can say, therefore, or thus, as blue photons carry more energy than red photons, 1 watt beam of blue light will have fewer photons than 1 watt beam of red light. And that's how you do the question, or that's how you would approach the question. You need to firstly explain what's the link between the wavelengths and how that affects the energy of the individual photon. And then that's where you can then make the link that even though I have the same amount of energy transfer of red light and blue light in that particular second in time, what that actually means is there's less quantity of blue photons than there are of red photons. So that concludes our explanation of this exam problem for today. If you found this problem useful, please like and subscribe, and I will see you next time.